The final talk for the session is a live talk. It's Thomas Rolinger talking about runtime optimizations for irregular applications in Chapel. Thomas, yep, you're all set.
All right, and you can hear me?
Yep, go ahead.
Okay. Oops. Okay, so I'm Thomas Rolinger. I work at the Laboratory for Physical Sciences, and I'm also a PhD student at the University of Maryland. So getting right into it, we'll give some motivation and background for why we're looking at irregular applications, what makes them interesting, what makes them hard to optimize, and we'll give an overview of the particular optimization that we look at, which is the inspector-executor technique. And then we'll go right into how we actually do this within Chapel, show a performance evaluation, and then conclude with some future work. All right, so motivation. So what we're trying to address is the memory wall. The speed at which we can get data from memory is outpaced by the rate at which we can operate on it. So for these memory-intensive applications, we're pretty much just waiting on memory all the time. Now, for an irregular application, this is even worse. So these are applications that have sparse and unstructured memory access patterns. So things you'd find in graph analytics, sparse matrix codes. Because they lack spatial and temporal locality in their access pattern, we end up with fine-grained remote communication, which is going to be the bottleneck for performance. And these applications are hard to optimize because these memory access patterns are not known at compile time. So we have to look at runtime information to do anything. And that leads us into the inspector-executor technique. So this has been out for quite a while. It's broken into two phases. Your inspector phase will take a kernel of interest and do some sort of analysis. So it can look at the memory access pattern, loop iteration dependencies. And then the second phase is the executor. So this takes the original kernel and it will generate a new version of it that's optimized using what the inspector found in its analysis. So it could reorder the loops, it could do data reordering, etc. So the idea is to get performance gains using these optimizations, we need to be able to amortize the cost of the inspector over multiple executions of the kernel. So the inspector is added to the original program, so it has some amount of extra overhead. So we're looking for kernels that don't change between iterations. That way we can run the inspector once and then reuse its analysis over multiple executions. So examples where this can be found are Conjugate Gradient, molecular dynamic simulations, and PageRank. And these are the three apps that we study in this work. And this is a compiler optimization. So the compiler can generate the code that performs the inspector and the executor. But for this preliminary work, we're doing things by hand because we want to make sure that there are actual performance gains we can get before we do all the work of doing it within the compiler. So moving along, how do we actually do this in Chapel? We'll be using this simple code as our kind of motivation. So this is a sparse matrix vector multiplied kernel, SPMV. A couple things to note, this for all loop is iterating over a block distributed array of rows. So each row in the sparse matrix is a record. And each iteration of this loop will be operating on a row on the locale where the row is stored. And this is the performance bottleneck in SPMV. This is the irregular indirect access to the input vector, which is X. And we're accessing it by the indices defined in this column index array. And this is not known at compile time because it's dependent on the actual sparse matrix you're operating on. So what we're trying to do with our optimization at a high level is to essentially eliminate all the remote accesses to the X array during the kernel. So what we're going to do is we're going to use our inspector to look at which column indices result in remote accesses to X for each locale that's being operated on in this loop. And so for any remote access we'll actually replicate the element that we're going to be accessing on the locale that needs it so we can have local access to it during the kernel. So this basically means we need a mapping from the column index array to the corresponding remote values of the X array. So to do that, we're going to be using associative arrays. If you're from Python, these are essentially dictionaries. So the keys in our associative arrays are going to be the column index values, which we'll just refer to as indices. And the values that they map to are the corresponding remote elements of X. So the advantages of using associative arrays for this, for one, they're a pretty clean way to store sparse indices. And for this particular use case, they are faster than Chapel's sparse domains and arrays. And an important key fact is that they automatically ignore duplicates, and we'll see in a few slides why that's important. And lastly, we can directly use the original column index values as lookups into this array, rather than having to change them to map to some kind of different compressed array format. But there are some disadvantages. In general, they have slower memory access times versus default arrays, and on a per element basis, they're going to be using more memory as well. And shown here on the right is what each locale is going to be storing to kind of represent its associative array. It's what we're going to call a sparse buffer. So examples of what this actually looks like. So on the top, we have the original SPMV kernel, and below it, we have the corresponding inspector. So a couple things to note, each locale's sparse buffer is stored within this locale buffer array, which is block distributed, so one element per locale. We store the start and end indices for each locale's local partition of X, and the associative domain we'll be operating on is referred to as SPD in this code. And so here's the real meat of the inspector. We're going to be taking out each column index on a row and looking at whether it is going to result in a remote access. So we're doing just a simple bounds check. And this is assuming a block distribution. We could use the .contains method on each locale's local subdomain of the X array, but we found that this has some pretty bad performance loss because it's more general. So in the future, we would like to be able to support this for more general distributions, but also keep our efficiency high. Another thing to note is that there is no remote communication happening here. We're simply just doing bounds check. And then the last thing is the associative domain, SPD, is going to be modified concurrently by multiple tasks. And this is because this for all loop is going to be spawning multiple tasks per locale. But by default, associative domains have parallel safety enable, so this is okay. But at the end of the talk, we'll talk about how this can actually slow things down and ways we can speed it up. And the last thing to mention with the inspector is this kind of micro optimization. So we're going to take each locale's associative domain. We're going to pull out the indices, the keys, and we're going to create a sorted array of those indices. In the next slide, we'll see how that helps. So here on the right is the corresponding executor. So this is the optimized version of SPMV using what the inspector just found. First thing to note, this block of code at the top is going to be performing an update or a gather of the original values from the X array to each locale's replicated copy. So this is because most likely the values in X have changed since the last time we ran this kernel. So we want to make sure everything's up to date. Another thing to note is that these are all remote reads, since clearly we're only replicating remote values. But since associative domains automatically ignore duplicates, we only store each remote value once, regardless of how many times it's actually accessed. So this is really the key fact of why we can get performance with the optimization. We can amortize the cost of a single remote read in this update routine with multiple local accesses during the kernel. And then going back to this idea of sorting the indices. So if we were to just directly iterate over the associative array or associative domain in this loop, we would get pretty bad performance because the indices are sorted or unsorted. And this leads to poor locality and Chappell's remote cache. So if we can sort them up front, we see as much as a 22x speed up versus not sorting. And this is total runtime execution, not just for this routine. And then lastly, here is the same type of bounds checking we did in the inspector. This is where we decide whether we should be looking up our value in the local associative array or getting it from the already local partition we own of X. So moving right along, here's our performance evaluation. In our paper, we looked at 3 different applications, but for the sake of time for this talk, we'll just be looking at the PageRank kernel. For our system, we have a 16-node InfiniBand cluster. Each node has half a terabyte of RAM and 20 cores. We use Chapel version 1.24.1, which has the latest InfiniBand optimizations that were discussed earlier today. That's important since we're using GasNet over InfiniBand. And for comparisons, we're looking at our baseline, so just plain optimization or no optimizations applied. And we're also evaluating against a replicate all approach. So this doesn't actually do any kind of runtime optimization. It's just going to give each locale a full copy of the array. And in the slides, we'll be referring to the inspector-executor as IE. So for PageRank, we looked at 2 real web graphs as well as 2 graphs from the Graph 500 benchmark. And their details are on the table here at the bottom. And so we're executing PageRank until convergence. And on the far right of the table, you can see how many iterations are required to converge given this tolerance and damping factor. One thing to note is the Graph 500 graphs, since they're so large on for the baseline, we can't really run them feasibly for the full number of iterations. They would take too long, at least for my standards. So we run them from 1 iteration for the baseline, and then we're going to extrapolate them to the full iteration runtimes. And as you can note, our graphs here are fairly large, I guess, depending on your definition of large. So the smallest has 630 million edges, and largest has 8.5 billion edges. So the first performance thing we can look at is the overhead of the inspector. So what percentage of the total execution time is spent doing the inspector. And so we found over all of the data sets and different locale counts that the average is about 5% relative to total execution time. So this is fairly low because there's a good number of iterations for each of these data sets to run to allow us to amortize the cost. So you can see here on the chart on the right, our bottleneck now after the optimization is no longer the kernel, but it's these updates that we're doing before the kernel. And we'll talk about at the end of this talk about what we're planning to do to address that. The other thing to consider is the memory usage. So since we're replicating data on each locale, there will be some increase in memory. So we found that the average increase for the inspector-executor is about 80% over the baseline. So this is pretty high, mostly because of these large Graph 500 graphs. If we just look at the actual real-world data sets, it's 42%. But then if we look at replicate all, it's a different story. Since we're replicating, the entire graph essentially on every locale, the increase in memory is 600%. And we can't even run the scale 28 Graph 500 graph on anything less than 16 locales because we run out of memory. And recall, we have 0.5 terabyte of memory per node. So replicate all is just not a scalable solution in those cases. So the key point here is we are replicating less data with the inspector-executor because we do this runtime analysis to find out exactly what we need rather than replicating everything. Then lastly, we have the runtime speedups. So these are relative to the baseline. So higher bars are better. In blue is the inspector-executor and orange is replicate all. We find that the average speedup for the inspector-executor is 11x and the average speedup for replicate all is 5x. So some of the key points here, the inspector-executor is faster than the baseline because we can exploit the data reuse in the kernel. So this is going back to that idea I mentioned where regardless of how many times we need to access a remote element in the kernel, we only have to do one remote get, and then we get, quote unquote, unlimited local accesses. Another thing to mention is because the inspector-executor replicates less data, we spend less time doing those gathers and updates before each kernel runs. So that's the reason why we generally outperform replicate all, especially on the 2 graphs on the top. Those are the real web graphs. But if you look at the Graph 500 graphs, then we actually find the inspector-executor is slower than replicate all. And this is because these graphs are essentially uniformly random in terms of their sparsity structure. So the inspector-executor ends up replicating pretty much the exact same number of elements that replicate all is doing. So at that point, what you're limited to in performance is the memory access costs to your associative arrays when compared to replicate all, which is using default arrays. And as we mentioned, associative arrays are going to be slower in that case. So other noteworthy comparisons to mention, like I said at the beginning, the baseline for 2 locales would require up to 20 days to run all the iterations for the scale 28 graph, but the inspector-executor can do it in 6 hours. And then if we scale up to 16 locales, we're looking at a difference between 41 hours down to 1 hour. So we're talking about taking applications from days down to hours. And here is a summary of the 2 other applications that were not presented here, but they're in our paper. The main thing to note here is the column on the far right. So this tells us for each application, the maximum number of iterations that we need to run to break even with the baseline. And as you can see, they're fairly low, which is good because it means we don't have to run some artificially high number of iterations before this optimization is actually applicable. So last thing is future work. What we're mainly doing right now is optimizing the optimization. So making the different parts of the inspector and executor faster. The first thing goes back to the inspector where we mentioned how we needed thread safety for this associative domain operation. But if we could formulate this for all loop structure as an equivalent code for all, then we have 1 task per locale, which is only operating. So only 1 task is operating on a given locale's associative domain at once. So we can turn off thread safety, which we found gives us as much as a 6x improvement in the runtime of the inspector, which was surprising to us because we're actually reducing the total amount of parallelism by doing this in a code for all loop. And generally, this transformation from a for all to a code for all can be done, but it's not always true. So as we move towards doing things in the compiler, this is something we're going to have to consider when this is actually a valid thing to do. The other thing is looking at those updates in the gathers. Like we saw with PageRank, it's now the bottleneck. So it's actually a prime candidate for using aggregation that was discussed earlier. So essentially what our CUDA does. So we're actively doing that. And we're also considering looking at using the default arrays instead of associative arrays. So this will give us more efficient memory accesses, but it's a little bit messy because it requires us to actually start changing the indirection array, that column index array in SPMV, to have different indices because they need to now map to a default array. So we start to lose the advantage of using associative arrays for not having to remap our indices, but we could get performance. So there's going to be a trade-off there, which leads us into the compiler automation. So we're looking at perhaps starting with user-driven pragmas. So identify the kernel of interest that you want to optimize and maybe the array itself. But there are prior works that can actually do static analysis to find suitable kernels for these type of optimizations. And then lastly, we're always looking for more applications to test. It's not ideal for us, the optimization developers, to be writing these test cases because we're just probably introducing bias. So we like to have more applications to test to make this more robust. So if you have anything that you think could benefit from these type of optimizations, then feel free to reach out to us. We'd be very interested in looking at those apps. So final conclusions, the inspector-executor technique shows promise for irregular applications in Chapel. We're seeing speedups as high as 224x, and we're talking about application runtimes going from days down to hours. And the other thing worth mentioning is this optimization doesn't really rely on low-level details to be exposed in the code. So we try to stick as close as we could to the philosophy of separating the algorithm from the data distribution. So our baseline implementations are very close to what you would see as the on-paper description of the algorithms. So that's promising to us because it means that a majority of the code written by non-Chapel experts could be applicable, or our optimization could be applicable to those types of codes. So I'd be happy to take any questions, and thanks for listening.
Thank you, Thomas. So we've got two questions from Brad, so I'll start with both of those. The first one is on how your results compare with existing results out there. And then the second question was something that I think you got to in your last slide, but maybe you'd like to say some more, which is how does your work sort of compare with the aggregator work that Elliot described for Arcuda? So, and how does it sort of contrast if you want to say some more about that?
Okay. So for the first one, it talks about how this compares to other things. I haven't done the comparison myself. I would probably guess we're a fair ways off, just because I don't have as much confidence that these baseline implementations were the best place to start, though I still think there's merit in showing that we can optimize these baseline optimizations or implementations to the point we can. But I haven't done any direct comparisons yet. That wasn't quite the initial focus of the work. Regarding the aggregation, as I mentioned, I think we've been seeing aggregation helping quite a lot in these update routines. We found that they're not candidates for the automatic aggregation that the compiler can now do, because it's a little bit ambiguous because we're using these associative arrays, but we can just do it by hand. And since we're planning on having this generated by the compiler anyways, I'm not opposed to writing fairly low level code that would ultimately be generated by the compiler.
We have one question, which was, are you using associative, just a question, just a clarification, whether you were using associative arrays in implementing sparse data. Can you elaborate on that?
Right. So the actual sparse data in terms of like the sparse matrix for SPMV, that's implemented in a fairly traditional compressed sparse row or similar like data structure. But for the data we're replicating, it is sparse in nature because we don't necessarily need to replicate all of the data. So, if you're thinking about what indices correspond to remote values, they're going to be a sparse index set. So that's why we use associative arrays for that. I don't know if that answers the question, but.
And then I think our last question is from Michael Ferguson, who asked if the compiler creates the inspector-executor as an optimization, would it only work for some kernels since it's effectively moving some gets earlier?
Right. So traditionally, the inspector-executor is a fairly targeted optimization that looks for these type of kernels where it has some sort of access pattern or loop ordering where it doesn't change. So I don't think this optimization could be applied to just any general kernel. But I think what we've found is we don't need a lot of iterations. In some cases, we're already faster than just doing one iteration. So I think there's some promise in looking at doing this in a non-iterative sense. But yes, in general, we are essentially doing a very large prefetch of all the remote data. And that's one thing we're curious looking at is inserting software prefetching within these kernels to see if that could help, because that would be a good trade-off between memory usage and performance.
Great. So let's thank Thomas again, and all the speakers in this session. I think we have another 15-minute break before our last session of the day.